In this video, we'll explore a common continuous probability model, the gamma. In general, the gamma model can be used to model a continuous random variable x that can take on positive values, that is, x is greater than 0. It's defined by two parameters, the shape s and rate r. Consider some examples. Let x be the lifetime in years of a light bulb. Further, suppose that the variability in lifetime from bulb to bulb for a certain brand of light bulbs can be modeled by gamma with shape parameter 2 and rate parameter 1. In this case, we observe that though most light bulbs will last roughly 1 to 2 years, there are some exceptional cases that last longer than 5 years. Compare this to the lifetime of a different light bulb brand, which is described by a gamma model with shape parameter 8 and rate parameter 2. This brand of light bulbs tends to last longer, with a typical lifetime around 4 years, and a greater proportion of light bulbs lasting at least 5 years. Consider another example. Let x be the time in minutes between phone calls coming into a help desk. Suppose that at the busiest time of year, the variability in times can be modeled by a gamma 1-2 model. In this case, we see an exponential drop-off in times, with there typically being somewhere around half a minute or a minute between calls. And it's highly unlikely that there would be more than, say, 2.5 minutes between calls. Comparatively, suppose that at the least busy time of year, the time between calls at the call center can be modeled by the gamma 1-0.5 model. Though there's still an exponential drop-off here, it's a bit slower. The time between calls is typically around 2 minutes, and it's relatively common for there to be more than 2.5 minutes between calls. Finally, if you've ever played around with an exponential probability model, these PDFs might look familiar to you. In fact, the gamma model with a shape parameter of s equals 1 and some rate parameter r is equivalent to the exponential model with rate r. For example, the gamma 1-2 model is equivalent to the exponential model with rate 2. These examples have given us a sense of the gamma model under different settings for parameters s and r. The formula for the gamma PDF formalizes these observations. If x has a gamma SR model, then the PDF of x is equal to r to the s divided by the gamma function of s times x to the s minus 1 e to the negative rx, where the PDF here is defined for positive x values. Further, the gamma function is defined as follows. If z is a positive integer, 1, 2, and so on, then gamma of z equals z minus 1 factorial. Otherwise, it can be calculated by the integral here. The plots here allow us to contrast various gamma PDFs and how they depend upon parameters s and r. In these plots, the solid vertical line represents the mean or expected value of x, and the dashed vertical line represents the mode or most plausible value of x. The shapes of the PDFs, along with the comparison of the mean and mode, illustrate that no matter the s and r values, gamma variables tend to be right-skewed with a mean that exceeds the mode. Further, the far left plots here again illustrate that a gamma model with a shape parameter s equals 1 and some rate r is equivalent to the exponential model with rate r. Finally, as we go from right to left across the grid of plots, the shape parameter s decreases, while the rate parameter r remains fixed. The corresponding impact on the PDFs reveals that the smaller s is in relation to r, the smaller the mean value of the model, and the smaller the variability. That is, the model becomes more and more squished around smaller values of x. Beyond visual comparisons and evaluations, we can describe the various features of a gamma model using numerical summaries. For example, the mean or expected value of a gamma model is calculated by S divided by R. The mode can be calculated by S minus 1 divided by R, when S is at least 1. Alternative equations exist when this isn't the case. Finally, we can measure the variability of a gamma model using the standard deviation equation here. These formulas confirm our observations from the previous slide, that since the gamma model is right skewed, the mean value will always exceed the mode. Further, the smaller the S is in relation to R, the smaller the typical gamma outcome, and the smaller the variability in outcomes. Let's apply these formulas to our light bulb example, plugging in our S and R parameters. For the first brand of light bulbs, here on the left, the average lifetime is 2 years, though a 1-year lifetime is most plausible. Comparatively, the typical lifetime is longer for the second brand of light bulbs, with an average lifetime of 4 years. Now that we've seen the gamma PDF in action, let's take a closer look. We can decompose the gamma PDF into 2 pieces. First, the kernel of the PDF captures the part of the product here that depends upon X. This is the heart of the PDF and its description of the variability in X. The remaining piece of the PDF is the normalizing constant. This constant does not depend upon X. Rather, it's simply in place to ensure that the PDF integrates to 1. As such, we don't have to carry around the normalizing constant. We can simply note that f of x is proportional to its kernel. This makes it easier to manipulate the PDF and to identify a gamma model from a given PDF. Let's do that here. First, suppose that a random variable x has PDF f of x, which is proportional to x to the 4th times e to the negative 5x for x greater than 0. This kernel, x to some power times e to the negative x times some constant, has the same form as the gamma kernel here. Thus, this is a gamma PDF. In this case, x is to the power of 4, or 5 minus 1, and x is multiplied by a factor of 5 in the exponent. Thus, x has a gamma model with parameters 5 and 5. The next PDF looks a little different, but it too is the product of x to some power times e to the negative x times some factor, where x must be positive. In this case, x is to the power of 0, or 1 minus 1, and x is multiplied by a factor of 2 in the exponent. Thus, x has a gamma model with parameters 1 and 2. Equivalently, since the shape parameter s equals 1 here, x is exponential with rate 2. Finally, though this last PDF almost looks like a gamma kernel, it's defined on the entire real line. Thus, since gamma random variables must be positive, the corresponding variable x here is not gamma.